California farmers are fuming over not being allowed to use new technology that they say could help lower your cost at the grocery store.
In California, one of the world's most productive agricultural regions, and thousands of robots are now being deployed on farms. This is ushering the biggest leap in farming yet. These machines can pull weeds and plant seeds, with robotic and artificial intelligence taking on controls filled on the right people. What does this mean for the future of agriculture?
Robots are coming to a farm near you. A new breed of robots will thin, weed, and eventually harvest fields.
Robots on farm. When the first light of dawn breaks over a field in America, it's not to the sound of roosters, but instead to the quiet hum of GPS-guided tractors. This is the modern face of American farming, a world where technology and tradition work hand in hand to feed a nation. Across the United States, agriculture is a story of scale and precision. In Idaho, where the volcanic soil is perfect for potatoes, farmers harvest over 100 million tons annually. They use certified seeds and sophisticated irrigation systems that deliver the exact amount of water needed, monitored by weather tracking technology. When it's time to harvest, massive machines gently unearth the potatoes, ensuring they are undamaged and ready for inspection by the USDA. But the story doesn't end with potatoes. Travel to California and you'll find the heartland of America's carrot supply, producing a staggering 85% of the country's crop. Here, the challenge is different. Carrot roots are sensitive, and soil compaction from machinery can reduce yields. Farmers carefully prepare deep, loose soil beds and tailor planting density up to 1.3 million seeds per acre, based on whether the carrots are destined for fresh markets or processing. The harvest is a marvel, as a single machine moves through rows, swiftly pulling the carrots from the earth in seconds. If human hands had to do this, it would take much longer. Yet, for all the advanced machinery, some of the most vital work is done by human hands. Automation is usually reserved for sturdy commodity crops, while delicate fruits require a personal touch. This is where the indispensable role of migrant labor comes in. In the pear orchards of Washington and the tomato fields of California's San Joaquin Valley, thousands of workers arrive at the peak of harvest. They work from the early hours of the morning, carefully picking plums and tomatoes, usually while the fruit is still green to prevent bruising. In North Carolina, the sweet potato harvest depends on nearly 3,000 migrant workers, who even earn premium wages on rainy days to speed up the harvest and prevent spoilage. These workers bring a delicate expertise that machines cannot replicate. But in the global agricultural industry, traditional methods still reign. In Indonesia and the Philippines, harvesters skillfully climb towering trees or use long poles to gather coconuts. Every part of the tree is used, from the water and meat for consumption to the husks for fiber used in ropes and carpets. From the technologically advanced fields of Idaho to the fruit pickers and coconut harvesters overseas, farming has changed over the years. At the center of technological advancement is California, which has released thousands of robots that would change farms forever. Technological revolution on farms. In California, there's a technological revolution going on in the fertile expanses of California's Central Valley, where almond orchards and citrus groves are growing. Farming here has long meant early mornings, long hours, and a shrinking pool of skilled workers. That's where the startup GUSS Automation comes in, with its driverless sprayers. Now, California is quietly becoming a proving ground for autonomous agriculture. Founded out of an orchard spraying business in Kingsburg, California, GUSS Automation responds to a pressing problem, which is labor. One grower realized that labor shortages were the biggest challenge he faced, and so he decided to build machines instead of waiting for people. Their core machine uses GPS, LiDAR, cameras, and pre-mapped orchard rows so that a single operator can supervise up to 8 machines from a laptop. It was a striking shift from 6 drivers in 6 tractors to 2 operators managing a fleet of robots. The results so far are more than just high-tech. At one farm in Kern County, the machines have sprayed thousands of acres over multiple seasons, delivering consistent spray rates, reliable performance, and fewer human error issues. From a farmscape perspective, the benefits are tangible. These robots reduce labor costs, cut downtime, avoid operator fatigue, and improve precision. Now, GUS machines cover about 3 million acres around the world. And in 2025, John Deere announced the full acquisition of GUS, signaling that the industry believes that this is the future. But it's not all plug and play. Running a fleet of orchard robots demands new skills. Operators must map orchard rows, monitor sensors, manage refills, and troubleshoot when the LiDAR thinks a tall cover crop is a moving obstacle and shuts the machine down. For some farmers, it took around 4 months and 2 to 3 spray cycles to fully understand and adapt. For California, where a small number of crops dominate and labor costs are high, automation is a logical step. But beyond efficiency, the robot farmers evoke something bigger, which is a shift in how we think about agriculture. The landscape holds computers, sensors, and fleets of autonomous machines. Of course, there are social and economic ripple effects. What happens to seasonal workers? How do small growers afford a $285,000 machine? How does regulation keep up, especially when keeping an operator on board? Although California's farming robots hold a lot of promise, the ag-tech sector in California is facing pressure. There's also a rise in different kinds of technology in California, aside from just the growing robots. Now, farms are using weed-killing robots to protect their plants better. Weed killer. Imagine driving through a cornfield, and instead of traditional sprayers blanketing the ground with herbicides and missing others, you watch an advanced machine glide through. The cameras scan each plant, and the software will decide whether to weed it or leave it. Those kinds of machines are now changing the game of weed control in agriculture. Let's start with See & Spray. Backed by John Deere, the system uses dozens of AI-powered cameras mounted on a sprayer boom to distinguish crops from weeds. Once the system recognizes a weed, it triggers a jet of herbicide only on that weed, dramatically cutting chemical use. This means there's less chemical drift, less environmental impact, and smarter resource use. What's more, farms that use this technology can map where weeds are dense, where they've been managed, and how to plan for the next season. Impressive, right? Then there's Laser Weeder, which takes it a step further. It's a machine that doesn't just spray less, but it burns weeds with lasers. Powered by deep learning and high-resolution cameras, it identifies unwanted plants and targets their growth point with thermal energy so precisely, you could argue it's surgical. We're talking about tens of thousands of weeds eliminated per hour, with no herbicides or heavy soil disturbance. One grower achieved an 80% reduction in weed control cost, with the machine paying for itself in a few years. What makes this technology so fascinating is the combination of artificial intelligence, machine vision, and mechanical and thermal intervention. First, the machine uses a library of plant and weed images. Next, it classifies each plant. Then, it finally acts either by spraying or zapping with a laser. In the case of Laser Weeder, up to 30 lasers can fire every fraction of a second to obliterate weeds at their roots, leaving their crops untouched. The result is a targeted approach to weed control. This is part of a larger shift in farming. As herbicide resistance grows, soils degrade, and labor becomes harder to find, farmers are now using precision tools to maintain yield and sustainability. What these robots offer is a way to do more with less. That means fewer chemicals, less soil damage, and potentially healthier harvests. As for large-scale farms, the economic draw is big. Of course, there are some challenges. These machines are expensive. They require solid data infrastructure like imaging and mapping, and human insight is still needed. For these weed killers, the AI models need to be trained on lots of plant data. Even if the machine doesn't need internet, it still needs clear sensors, good lighting, and a well-mapped field. Also, farmers must consider repair, software updates, and adapting workflows. While California is just setting up its agro-robots, China is a step ahead with its fully robotic farm. China's robotic farm. If you step into China's robotic farm, you can see drones overhead and enormous driverless harvesters gliding across the stalks, unloading food into trucks without human hands. This is happening right now in Qingfeng County, Henan Province, where a 233-hectare farm has become the first unmanned wheat-corn rotation farm. In this space, machinery is what takes care of planting, irrigation, monitoring, and harvesting. Intelligent machines prepare the spoils, while robotic planters ensure uniform seed distribution, drones patrol for pests and stress, and a central operations room monitors every micro-detail of the land. After this, irrigation labor dropped by 90%, and what used to take 10 people can now be handled by one person on a smartphone. What gives this robotic farm its power is the connectivity and data. The machines rely on China's Beidou navigation satellite system for high-precision positioning, drones stream imagery to the cloud, and AI-driven models forecast crop growth and irrigation needs in real time. For instance, the drone patrol collects data at 10 points every 30 minutes between 9 a.m. and 3 p.m., feeding algorithms that will then tweak fertilizer, water, or spray timing accordingly. The results speak for themselves. Harvesting time fell from 7 days to 4. Overall labor cost dropped by 40%, and yield increased by 20% compared to neighboring conventional farms. The farm is now a testbed for what smart, sustainable agriculture could look like in China and beyond. Previously, traditional farming meant hands in soil, long days, and many workers. This new model is about remote monitoring, predictive analytics, and machines doing the grinding work while humans oversee from afar. At the control center, drones, autonomous vehicles, and data can be arranged in one location. But China is still facing some challenges in keeping this farm running. It requires large capital investment, robust sensor networks, high-quality data, and reliable connectivity. Smaller farms that are located in rugged terrain or lacking infrastructure are finding it difficult to adapt. There's also the human resources dimension, as farm laborers are losing their jobs, and technology is affecting local communities. Still, it seems like agrotechnology is the future of farming, and these problems would have to be solved over time. Different forms of farming technology have seamless operations that take care of what men would take longer to do. Operation with technological advancements, onboard computers already know the field map, row spacing, and the seeding pattern based on previous seasons. With millimeter-level precision, it drills furrows, places each seed at the right depth and spacing, and then retracts to let the next module step in. This is engineered planting. Researchers now have systems built for planting, weeding, and harvesting. They all share common components like sensors, actuators, onboard controls, and localization systems such as LiDAR, cameras, and IMUs. After planting, the system switches to monitoring mode. Drones are equipped with multispectral cameras, and ground robots are equipped with soil sensing technology. They sweep the terrain to collect gigabytes of data on soil moisture, nutrient levels, and crop health. Machine learning algorithms will analyze that stream of data, detect stress or pest pressure, and feed the insights back into the machinery. If a patch of field shows less moisture than expected, The irrigation robot will move to the spot to take care of it. It can also schedule a nearby fertilizing companion to act. Then there are weeding robots. As rows of growing crops increase, a semi-autonomous vehicle will travel between the rows with a high-resolution camera and AI-driven vision systems. Its software can differentiate crop plants from weeds based on shape, color, and texture. Once it's identified, the robot will trigger a precise mechanical blade or localized herbicide jet, or in cutting-edge cases, a micro laser that zaps the weed's stem. Scientists have shown this can reduce chemical herbicide use by up to 70%. When harvest time arrives, there are different robots for these. Autonomous harvesters can be equipped with vision systems to identify ripe produce based on their color, size, and even thermal signature. They drive along predefined routes, pick quickly, and sort directly, sometimes even unloading themselves. Machines don't get tired, so they can work day and night and complete tasks. All these machines aren't standalone, but they're connected. Data platforms compile information from tractor sensors, drone imagery, and soil monitors. Farmers and farm managers monitor dashboards, tweak parameters, and manage the fleet of robots as if commanding a factory rather than a field. The terrain is mapped, the rows are logged, and the obstacles are detected. Some key technologies that are making this transition much easier include GPS navigation systems, autonomous navigation with LiDAR and IMUs, sensor fusion, and online control systems. Farming doesn't depend on brute force intelligence anymore. Instead of general spraying, it uses blanket fertilizing and rote planning. This technology enables targeted actions, eventually improving efficiency and reducing waste. The farming soil needs to be responsive to what each plant actually needs. Integrating agrotechnology into a farm isn't trivial. Farms must manage data interoperability, machine maintenance, operator training, and upfront investment, but they are still facing different challenges that make it difficult to implement technology. Challenges. The idea of robots transforming agriculture is exciting, but when you look closely, there are major challenges that affect that excitement and development. One of these is the financial hurdle. Advanced farming robots like autonomous tractors, smart weeding machines, or precision seed planters come with hefty upfront price tags. Many small and medium-sized farms don't have the capital to invest in these systems, especially when their margins are tight. It's one thing to buy the machine. It's quite another to ensure payoff, and in many cases, the return on investment isn't immediate or guaranteed. There's also the problem of technical complexity and maintenance. These machines rely on software, sensors, GPS/RTK cameras, data links, and intricate control systems. Any breakdown, such as software glitches or malfunctions, can halt operations. Any technical failures or malfunctions could disrupt crucial tasks, leading to losses in crop yield or operational downtime. A related issue is environmental adaptability. Farms are messy, variable places, changing soil, mixed crop types, uneven terrain, dusty or muddy conditions, variable lighting, and weather surprises. These conditions challenge machines that may perform well in controlled settings, but struggle in the real world. The practical consequence was that a robot was working flawlessly in China, but was struggling in the real world. Technology now integrates existing systems and practices for future friction. Most farms always invest in tractors, sprayers, and management systems, and the workflow is built around people. Building a robot means one needs to rethink logistics, training staff, and even retrofitting infrastructure. Then there's the human dimension. Many farmers have honed their methods, rebuilt trust in their equipment, and may be skeptical of unfamiliar technologies that demand new skills and shift their role from hands-on driver to remote supervisor. Another complex aspect is infrastructure and connectivity. Systems that have been relying on GPS, satellite links, cloud analytics, or 5G/4G connectivity may stumble in remote or poorly connected farmland. On top of this, there is the data and operational risk. These machines collect masses of data, require data storage, sometimes cloud platforms, and introduce concerns over data privacy, cybersecurity, and system reliability. If the system suddenly fails, it's not backed by support. Lastly, the challenge of scaling and accessibility looms large. The large industrial farms may have the budgets and the infrastructure to adopt robotic systems, but for smaller farms, the gap remains, or may even widen, leading to concerns about inequality in agricultural productivity. Despite all these challenges, there have been successful cases. Successful Robots AI is now transforming all the stages of farming, whether it's to plant, water, weed, or fertilize crops with precision. What once required human labor is now managed by advanced machines that plant, water, weed, fertilize, and harvest crops with precision and efficiency. The rise of robotic farming marks a major shift from traditional practices toward a system defined by automation, data, and sustainability. Artificial intelligence and machine learning form the foundation of this revolution. These technologies allow robots to analyze soil conditions, weather patterns, and crop health to make data-driven decisions in real time. Machine learning makes it easier for them to adapt, predicting pest infestations, identifying ripe crops, and optimizing farming operations. Artificial intelligence and machine learning form the foundation of this revolution. These technologies allow robots to analyze soil conditions. Machine learning enables them to adapt to predicting pest infestations, identifying ripe crops, and optimizing seeding patterns for the best yield. Combined with GPS navigation, robots operate around the clock, performing tasks like weeding, planting, and harvesting with pinpoint accuracy and minimal waste. The use of robotics in agriculture enhances productivity while conserving resources. Robots can work 24/7 without fatigue, ensuring that every stage of crop growth is managed precisely. Irrigation systems, guided by sensors and AI, deliver just the right amount of water to each section of a field. Fertilizing robots analyze soil health and apply nutrients only where needed, preventing overuse and protecting ecosystems. Weeding robots use image recognition to distinguish crops from weeds, applying herbicides selectively to reduce chemical usage and preserve soil health. When California released thousands of robots to farm the land, it shocked many in the agricultural industry. But this isn't the first time, and other states are also making moves to fight against agricultural support in that area. Meanwhile, places like China are already hard at work building fully integrated systems for farming. What do you think about robots replacing jobs in farming? Let's know your thoughts in the comments. Thanks for watching this video, and we will see you in the next one.